Well, this is exponential day, the day for the function that only calculus could create. Y is e to the x. And it couldn't have come from algebra, because however we approach e to the x, there's some limiting step. Something goes to zero, something goes to infinity. I've got different ways to reach e to the x, but all of them involve that limiting process, which we haven't discussed in full. Let me come back at a later time to the whole theory, discussion of limits, and just go forward here with this highly important function. And I'd like to start with its most important property, which is, so it has this remarkable property that its slope is equal to itself. That's what is special about e to the x. Its slope is equal to the slope is equal to the function. Now, I have to admit that if we had a function like that, y equal e to the x, then 2e to the x would work just as well, or 10e to the x. Those would, the factor 2 or the factor 10 would be in y, and it would also be in the slope, and it would cancel. And this is a differential equation, our first differential equation. A differential equation is an equation that involves, as this one does, the function and the slope. It connects them, and that's the fantastic description of nature, is by differential equations. So it's great to see this one early, and it's the most important one. When you get this one, you've got a whole lot of others solved. Okay, but I needed to give it a starting point so that the solution would be e to the x and not 10e to the x. So where shall I start it? Well, if I want it to be an e to the x, then when x is 0, e to the 0 power, some number to the 0 power, is always 1. So let me start this. Y equals 1 at x equals 0. Differential equations, you have to tell where they begin. So that's our starting point. And do you see what this means? This means that it starts at 1, and what's its slope at the starting point? The slope is also 1, so it's climbing. As it climbs, so y gets larger because it's got a positive slope. As y gets larger, the slope gets larger, so it climbs faster. And then it's gone higher, y is bigger, the slope is equal, so the slope is also bigger, so it climbs even faster. It just takes off. It climbs much faster than x to the 100th power. You might take y equal x to the 100th. That's climbing pretty well. 2 to the 100th, 10 to the 100th, but no way, it doesn't come close to keeping up with y equal e to the x. Okay, I've got several things to do, and one more thing I have to do. This is a key property, but there's another key property that is true for any 2 to the x, 3 to the x, e to the x. And that key property is also to show, I have to show this, that my function, e to the x, times e to the possibly a different x, is equal to, do you know what we want here? This has got to come out of the construction, out of this property. It's got to come, but we want this to deserve to be called some number to the x power. If we take some number x times and multiply it by that same number, capital X times, then we've got that number how many times? x plus capital X. This is what, so that's a key property to be proved. So what will I do? Let me summarize in advance, outline in advance. I'm going to construct this function from its property. Then I'm going to check that it's got this property, that important equality there. Then, of course, I'll graph it, I'll figure out what E is, and I'll say something about cases where this comes up. Oh, I could even say something right away about where does this happen, that growth is equal or proportional to the function itself. It happens with interest, with money in a bank. When you get interest, the interest is proportional, of course, to the amount there. And if they add that interest in, if you don't take it out and spend it, but you compound it, put it in there, then you have more money. When they compute the interest again, it's computed on that larger amount and is more interest than the first time. And so it goes. So that's, money in a bank is a case, it's a case of exponential growth. A hedge fund goes faster than our bank account does, but all following e to the x. If you just hang on long enough, you're way up there. Okay, so here's my job. Follow this rule and start at y equal 1. So can I just do it this way? Here's my function y of x that I want to construct. I want to build that function, and I know that it starts at 1, but it's going to have some more things. Now this has to equal dy dx. These have to be the same. That's my rule. So dy dx is going to start with a 1. But now I can't stop, because if the derivative is a 1, I have to put an x up here so that its derivative will be 1, right? Its slope will be 1. That's that steadily climbing x whose slope is 1. But now these are supposed to be equal again. So I have to put this x also here. But now I've got to add something more on the top so that the slope will be 1 plus x. The slope of the x was 1. What do I need here to give the slope to be x? Remember, x squared had the slope 2x. So I need half of x squared so that I'll have 1x. So I need a half of x squared. Good. The slope of that is this. But I'm also trying to get the two to be equal. So I have no choice. I have to put in the 1/2 x squared there. You see, I'm never going to catch up. Or only if I go forever. That's the point. I'll have to go forever. And what will the next one be? Oh, yeah. If you see the next one, then we can see the pattern. So it's going to be, now what am I doing? This one has to have this slope. I'm trying to I'm fixing the top line now. If I'm aiming for a slope of x squared, then I need some number of x cubes. So how many x cubes do I need? Well, I need to know what's the slope of x cubed. The rule for powers of x to the n, is n times one smaller power. The slope of x cubed is 3 times x squared. So I had better divide by that 3, so that the 3 cancels the 3. Now the slope of that, the 3x squared, the 3's would cancel and I get x squared, but I'm looking for 1/2 x squared. I need also a 2. Do you see that it's 1/6 of x cubed that's going to do the job? 1/6 of x cubed. Because the slope, the 3 cancels the 3, and I wanted to end up with a 2. And now, you know what's coming? These are supposed to be equal. I have to have this 1/6 x cubed down here too. And I never get to stop. Can you see, we have to see, okay, what is a typical, after I've done this, say, n times? I'd like to have some idea of what is it when I get up to x to some nth power. Then it's multiplied by some fraction, and I'm looking to see what is that fraction. What is that fraction? And then, of course, they'll all show up down there again. Well, if you see this pattern, this was 3 times 2. You could say 3 times 2 times 1. This one was 2 times 1. This one was just 1. It's n factorial. N factorial is what I need. I need n times n minus 1. I need all these numbers all the way, and I'll throw in the 1 at the end. And I have to put the mathematicians' take it away symbol, the little 3 dots that mean don't stop, keep going. But do you see that this will be okay? This is called n factorial, x to the nth over n factorial. Because when I take the slope of x to the nth, an n will come down, cancel that n. X, I'll have 1 lower power. Do you see when I take the slope of this, I'll have the n will cancel the n, so I'll still have these other guys down below, and I'll have x to the n minus 1, and that will be x to the n minus 1 over n minus 1 factorial. That will be the previous one. But now I have to add in the x to the nth over n factorial, because y and dy dx have to be the same, so I have to keep going. Okay, so you might say, well, you're going to blow up. Not personally, the series. But what saves you? What saves you is the fact that these n factorials, those fractions, that n factorial gets to be really large really fast. Faster than this x to the nth could grow. So altogether, these terms, x to the nth over n factorial, they get extremely, extremely small. And then this series of things comes, it comes to a limit. It doesn't keep going, getting bigger and bigger and bigger as I add more terms, because what I'm adding is so small, so small. And that's the point where we have to discuss limits later. Okay, so that's my construction. Construction complete. The function y to the y of the exponential function, e to the x, this is e to the x, is being defined by 1 plus x plus a half x squared plus a 6x cubed, and so on. Okay.